one of the nice things about everyone using cell phones or watches nowadays is that everyone should have exactly 320 on their clocks right now. So we're going to go ahead and start. You're in NetVC. I'm going to point out the note well. I know it can't be read on this screen very easily. It's in the, it's up on the website. If you don't know what this means, step out in the hallway and talk to anyone else out there. I'm sure they can explain it to you. Basically, there are implications about IPR that are implied by IETF process. You should be familiar with them if you're going to speak in this room. And we have some administrative tasks here. Mo has already dropped off the blue sheets. They should be circulating. Make sure you sign the blue sheets before you leave. And we need note takers. I would like a primary note taker and a backup note taker, preferably. And we don't need a blow-by-blow of what is said. We simply need someone who is willing to transcribe any decisions or action items corresponding to this meeting. This shouldn't take an awful lot of your time, just enough to record those things. I know. And anyone that I would call, like, he's going to be busy presenting. Nathan, you actually are presenting tomorrow, right? You could take minutes? Okay, thanks. And Jonathan, can I impose on you to also record these just in case? Awesome, thanks. And the final thing I'm going to ask for is someone to sit around in the Jabber room in case we have remote participants who want to say something and take their comments to the microphone. Awesome, thank you very much. Okay, that's it. Let's go ahead and get started on the agenda. If anyone has comments about the order and topics here, go ahead and raise them. We're going to go through the requirements document, talk about the tests document, and have some discussion of the new de-ringing filter that we've been playing around with recently. If anyone has comments on this. All right, and then just a couple of small things that Mo wanted to mention about.
So before we get started on the presentations, wanted to bring your attention to something we circulated recently on the mailing list. The IESG is looking at a proposal for new work called Cellar. It's a new work group that's going to be focused on lossless coding for archival applications, both audio and video. And we forwarded it. We forwarded that notice from the ISG to the NetVC list because we thought that some people in the room may also care about lossless coding. It's clearly outside of the charter of NetVC, so that none of the work would be done here. But we thought a lot of the people may have common interest between the two work groups. So if you are interested in that, please give your feedback to the ISG about that effort, and you can review the charter and give your comments there.
Yeah. The one thing I'm going to highlight about that in particular is that they are going to do a container format based on Matroska. So if anyone has interest in that, especially as it pertains to like NetVC, you want to keep your eye on it.
Yeah, and again, to clarify, it was audio, video, and the container and transmission. So storage, transmission, and coding all rolled up into that one work group. And the deadline is November 9th to give your feedback. So that's right after this meeting, right after this meeting ends on Monday.
Okay, and with that, I'd like to go ahead and call Jose up. Thank you.
Good afternoon, everyone. I'm Jose Alvarez. I'm actually presenting this requirements document on behalf of Alexei Filipov, who could not be here. So today I'd like to talk about requirements for the video codec and then make some comments on evaluation methodology, but Thomas is going to expand on that in his presentation. Next one, please. So just to give you an overview, just going to talk about some applications that we're considered for requirements, evaluation methodology briefly, and then conclusions. Next, please. So it's handful or thereabouts of applications that we are considering here in the requirements. Essentially, the first one is Internet Protocol Television, and IPTV is an overused term, and it's caused a lot of confusion whether it's over managed networks or not. What we really mean is IP delivery of television content. Then also video conferencing, video sharing from device to device, from mobile devices, or UGC, user-generated content. Screencasting, where you'd have essentially graphical information that it's being transferred on wireless displays, perhaps. Game streaming, very popular nowadays. And then finally, surveillance and video monitoring. So that's just to give you a flavor of the applications. And then I'm just going to go on details on that. Next, please. So on Internet Protocol Television, IPTV, essentially we put this together with OTT, meaning over-the-top services. And these are basic requirements. It's random access to pictures so that there could be easy access. And that random access varies. The RAP, the random access period, it should be small enough so that you can have accessibility to the video streams, and it could be anywhere from 1 to 15 seconds. Temporal frame rate scalability so that we can change frame rates dynamically, and error robustness. There's been a lot of talk about error robustness in the male reflector, but this is essentially for delay critical over-the-top transmissions. Optional requirements is SNR scalability, that's quality scalability. Today, for instance, if you look at other codecs like HEVC, there's a small, well, relatively small penalty if you use temporal scalability, about 3 to 5%, but SNR scalability is another issue, so we put them as optional requirement. Next, please. So you're going to be seeing a lot of several of these slides where we list all of the resolutions just to give you an idea of what we are talking about. In this case, for Internet Protocol Television, because there is some legacy material, we have included interlace. And interlace has been always a big topic for a long time. We don't really mean to say that we will have interlace tools at all. This is interlace handled mostly at the system level, where you typically have a deinterlacer and then convert your interlace material into progressive, and that's really what you code. But this is just to acknowledge that there is content that it's already there and needs to be handled one way or another. And then picture access modes, frame rates, and resolutions is what you will be seeing in this type of slide. Next, please. Next application is video conferencing. Video conferencing really is low delay, and low delay is as low as possible. And there's been a lot of discussion as well as what does it mean to have low delay. Really should be less than 100 milliseconds, and that's typically what we are suggesting. Again, temporal frame rate scalability and robustness are required for this type of application. Sorry. And we went off. Okay. That's bad temporal scalability. Yep, this one. Oh, previous one. Okay, and then optional SNR quality and also resolution scalability. Next, please. Right, and these are the rates, 15 to 30 to 60 frames per second for video conferencing, and picture access mode is just the first picture. Okay, next, please. Video sharing. This is from device to device. GoPro cameras, user-generated contents, that type of applications, where you want to have random access to pictures for downloaded video data. Again, temporal scalability and SNR scalability. Here in this case, we believe that it's useful to have SNR scalability as a basic requirement, as well as error robustness. Next, please. Yes.
Just Mosinati, just from the floor. Just going back real quick to video conferencing.
Yeah.
I think back one more, Adam. I think sorry, forward. I didn't realize. Traditionally when we have, traditional conferences where mixers are involved, then typically there's not many intro pictures ever. So the just first makes a lot of sense, but I think if you look at more of the use cases that are coming up now where there's a lot more switching than mixing, especially in PERT cases where it's all switching, intra becomes more important. And so I think we may want to consider heavier focus on intra, or at least a regular interval where we expect intra pictures to be switched in, average active speaker times for the video conferencing test sequences. Maybe we should define that in the common test conditions. So
some random access.
Yeah, not for random access sake, but for active speaker switching, we should have the test set for video conferencing should reflect modern active speaker switched conferences, whatever we think is a reasonable intra interval for that should be.
And what period is that usually?
I don't know a number off the top of my head, but it's
because in the test conditions we should have.
Yeah,
that, right?
The test conditions should definitely have something that reflects those kind of conferences.
If we could just have that question to the audience, maybe we'll discuss it in the mail reflector. Okay, thank you. Yes, Tim.
Can you maybe propose a number to the list, Mo?
Yeah, I'll find a way to find a good number. I don't
Right.
remember.
Yeah, I think that's a great idea. Thank you. Right, next, please. Video sharing. Oh, okay. Yeah, next, please. Right, so that's the resolution for the video sharings. We took this from a support page from Google. So if you'd like to amend these resolutions and frame rates, please let us know. But quite a bit of flexibility on the frame rates, because you can never know what device you're using. So from phone to phone, you need to have that flexibility. Yes, next, please. Screencasting. So that's the application where you have mostly graphical data or web pages or PowerPoint presentations on the computer display, and you'd like to be able to transmit those. So obviously that's really low temporal frequency. So not really very high rates, but really a lot of, very high quality. So we would like to support obviously RGB, which is 444 naturally. And so that's where, we say we have, so far we haven't really paid too much attention or have mentioned actually chroma formats. But for this one, 444 is very important, as well as 420 and 422. 422 is a little bit less of an important color format because it's traditionally being used for the broadcast industry. So it's either 444 or 420. High visual quality, obviously, it's important, either visually lossless or mathematically lossless. And optional requirements is error robustness. Usually these are for wireless displays. And so error robustness may not be a big issue then. Next, please. So naturally, a lot of the graphical type of resolutions are included, and multiple frame rates. But, the frame rates are one thing, but really there's not a lot of motion in these type of applications. Picture access mode is a little bit of multiple requirements where you have just intra frames or maybe random access, or simply just the first picture if you just want to transmit something that has been previously recorded. And the color format, as I said, is 444. Next, please. Yes, games. Sorry, yes, please.
One comment on the previous one, Jonathan
Yeah.
Lennox. There's many use cases of, I guess you could call screencasting. I mean, this is like where what you're sharing is not a full computer monitor, but one application window. One of the consequences of that is you get arbitrary image sizes, with including, odd numbered image sizes, which is problematic for a number of existing codecs. So maybe we should have something of that as something in the list.
Sure, that's a good point. We can add it as a comment there. Yeah. Okay, thank you. Next, please.
Can
So Peter
Yes.
Thatcher, I mean, if you're going to be covering desktop sizes too, they go up to 5K now. So
I'm sorry?
I mean, if you're going to be doing full desktop sizes, they can go up to 5K. So
Yeah.
need bigger numbers.
So different resolutions, right? Okay. Game streaming, very popular. It's rather big. One of the YouTube channels that it's the most popular is game streaming. Live play, for instance, is quite popular. And so the basic requirements is we want to provide random access to pictures, temporal scalability and error robustness. And optional requirements is really SNR scalability. But really it's very important to support this type of application. So the difference here is that the content is high frame rate potentially, and it has very sharp edges. And so it's a little bit beyond screen content coding. So screen content coding doesn't necessarily address this, but game streaming from a codec perspective needs to be handled specially. And next, please. And then finally, video monitoring and surveillance. So this is random access to pictures for downloaded video data or even live video data as well. The random access point is anywhere from 1 to 5 seconds, so it's a little bit shorter than other applications. And having a low complexity encoder at the expense of coding performance is important. One very interesting optional requirement that we see is support for high dynamic range. So far, the high dynamic range has been supported for other applications. But in this case, high dynamic range for video surveillance becomes really important because it helps your video analytics algorithms. And so details that are buried in the dark areas surfaced out, and then it improves your intelligent analysis of video. So for this application, we see that having high dynamic range could be very, very useful. Temporal resolution and quality scalability also it's an optional requirement, but this usually comes at a cost. And next, please. These are just multiple frame rates for video surveillance. Typically, you want high quality, but you don't necessarily want high frame rates, and so that is reflected in the requirements. And various resolutions typically tied to remote cameras. Next, please. So far we've outlined some basic requirements and some optional requirements. And next, please. So on the basic requirements, yes.
Sorry, I just got what? Yeah, my name is Martin Davis, but I'm commenting for somebody called it's a bit cut. Marivi on Jabber, who says, from an earlier slide, I'm concerned even 100 millisecond will be too high for real-time use. There can be slower modes for non-real-time use cases, but 30 millisecond or less for real-time needs to be the upper bound.
Mm-hmm. Okay. Well noted. Okay, basic requirements. So this is just a summary. First, on coding efficiency and compression performance. This is, it's basically saying what the charter says, right? I mean, it should be better than for the state-of-the-art video codecs. Today, input source formats, 8 and 10 bits are requirements. Color sampling formats, as I mentioned before, 444 for the wireless displays and screen content coding, and 420 for others. And coding delays, we believe that there should be support for low delay configurations. And so that's directly to that comment. So the delay should be I don't know, 320 milliseconds to 100. And then obviously there's comment on that it should be even lower. Next, please.
We have a comment at the mic.
Ah, yeah.
Mosenat again from the floor. So I think when we were looking at the requirements last time, there was a thought about trying to build, I guess maybe profile, for lack of a better word, figuring out some kind of proper profiles for these sets of requirements, and where would we start the work, where would we focus first, and what would we layer on afterwards. It seems like it may start to be time to get a good picture of that and get feedback from everyone about what they would like to see as mandatory requirements for all the candidates to support, and then what would be the optional profile, or what would be the optional features in the higher profiles. I think we should probably get some agreement about that pretty soon. And on the delay, I explicitly remember having a test condition of 0 structural delay. So not even 100 milliseconds, but literally 0 structural delay in the lowest delay setting. So I think we need to get some kind of alignment between what the requirements dictate as these profiles or these common conditions, and then what the test conditions describe as, here's all the common test conditions that we're going to test all these candidates in.
Right, exactly. So that's great. So the two comments. First, the second one. Yeah, there's been a lot of discussions on 0 delay means 0 delays, really, and that's really the lowest delays that you can have. So I think that we should reflect that as well. And on the profiles, if you look at the document, we have started to write down some profiles as well. But I totally agree that that will guarantee that decoders will be able to decode what encoders encode.
Yeah, and then one final thing I forgot is on the bit depth. A lot of the newer work, regardless of the input bit depth or the output display bit depth, so regardless of your capture or render devices, there's a trend towards having higher internal precision anyway. So having higher bit depth just for coding gain outside of requirements, outside of needing to handle input formats that are 10 or 12 bit. I think it may be good for us to differentiate those two things, and maybe build some of the candidates towards higher internal precision, even if there's not a 10-bit or 12-bit input requirement.
Right, exactly, and that's yeah. Other teams are doing similarly. Yes, right. And these are, I hope, that being taken in the notes, so I appreciate it. Next, please. Complexity, again, as I mentioned before, this is meant to be in line with the charter. Complexity, feasible real-time implementation for both the encoder and the decoder. Of course, we have to take a look at software implementations, but also hardware implementations based on state-of-the-art platforms today. We would like to have temporal scalability for sure. Hopefully, there will be a very small penalty in the encoder. And error resilience. And by error resilience, we mean tools that are complementary to the protection mechanisms that are already implemented at the transport level. Next, please. So this is in line to Mo's comment. So input source formats, bit depth, perhaps up to 16 bits per color components, color sampling, 4:2 optionally. It's very much used in the broadcast industry, as I mentioned, but for our applications, I don't think it's very important, but certainly RGB for those cases for screen content coding. Another optional requirement would be
clarification
support for an
is,
alpha channel. Yes.
Clarification, does RGB there refer to RGB 444?
444.
Okay.
And the only reason we put it here is that it only shows in the screen content coding case. Support for an auxiliary channel, an alpha channel, that's sometimes very, very useful for some applications. And high dynamic range, as I mentioned, in this context, we believe only for video surveillance, where it will help the analytics. Optional requirements for scalability, it's resolution and SNR quality scalability, and perhaps computational complexity scalability, where the complexity decreases along degrading picture quality, obviously. And that I mentioned also earlier in the low complexity mode for video surveillance, where it's okay to compromise on the coding performance if your encoder is going to be much simpler. Next, please. Following along with the optional requirements on complexity, these are tools that enable parallel processing, and other encoders have supported in the past slices, tiles, wavefront propagation processing. All these are highly desirable for to manage the complexity, and that leads to high-level multi-core parallelism in line with supporting devices that are common today. Especially entropy coding and decoding. Perhaps you allow multiple frames or subframe regions. And this is just suggestions, but that's really the requirement is really that we have flexibility in the complexity and that high-level multi-core parallelism. And perhaps even the low-level instruction set parallelism that favor architectures like GPUs. Again, these are all optional requirements. Next, finally. So the compression performance, yes.
Sorry, Martin Durst, Yamagakuin University, speaking for myself. For the requirements, one thing I have been using video recently, and one feature I used was that you can actually have the video run faster or slower. So there's lots of interesting videos out there, but if they're a bit faster, you get through them quicker. So how is that included in temporal scalability, or is that something that would be done, have to be done separately, or?
It could be included in temporal scalability, yes. Yeah, where your frame rate changes dynamically. That's what you mean.
Okay,
right?
but
Yeah.
you have these frame rates at like 15 and 30 and 60, but usually if you want the video going faster, maybe you want to have it just a little bit faster, like 1.2 times fast the speed or so. So yeah,
that's interesting. So so
if you want, I can after meeting I can
Yeah.
show you an example.
No, absolutely.
Okay.
We've seen cases
Yeah,
like that. What is the application for that? I mean,
Well,
other than
the
controlling
application
buffering,
actually
right?
it's used is I'm giving a lecture in English to Japanese students, and the university staff is taking that on video, and then the students can actually go later and review the lecture,
Sure.
and they can go through it faster or slower, as slow as they need, and so on. So that's the case. But I think there's lots of cases out there. I have often thought that like a presentation like this, if I want to go through offline, I can just speed it up a bit, and then
Right.
I save
Typically,
some
what I've
time.
seen is that those usually are just factor of 2, factor of 1.5. So those are predictable factors, right? Or is it infinitely variable?
No, well, the one that I know is has 1.2 and 1.5 and something like that. Yeah, it's definitely fixed.
Okay, great.
Yeah.
Okay, and this is about the methodology of compression performance evaluation and equality assessment.
Sorry,
Yeah.
just have another one. Thomas Davis, maybe. He wants me to say, what does support for HDR mean in practice? If you can do 10/12-bit, then with a mapping function and suitable metadata, then you can do some form of HDR.
Yeah, that's a good comment. Again, we want to put it as a requirement as in general high dynamic range, meaning that we should have a means for having pictures that are representative of high dynamic range. Surely, if you have more bits, obviously you can you can do that, but it's not necessarily linearly, right? So what we really want is also to be able to bring out the details in the shadows, if you will, in a nonlinear way, so that as I mentioned, to video surveillance applications, that will bring out the details. But it is a good comment, and it could be implemented that way. We're not suggesting any particular implementation, but just the usage of such techniques. And yeah, so here on the compression performance evaluation, methodology of compression and quality assessment, we only mean to say that there has to be objective evaluation and subjective evaluation. The details, I think that Thomas will deal with, but we put some slides here that have some examples, and that's what you're going to be seeing in the next few slides. Next, please. So obviously the requirements that we put in don't make sense if we don't have a way to check them properly. And so in this draft, we just put some high-level evaluation framework that we propose, but I think that eventually all of that should move into Thomas's document. Next, please. This is an example of a very commonly used Biontegard delta rate, BD rate comparison based on PSNR. Next, so and this I just want to point out that it has to do with establishing low bit rates, mid range, and high range, and then a comparison based on a reference encoder. Very much in line with what everybody else does. Next, please. And this is just about quality assessment on PSNR, peak signal to noise ratio, and then multi-scale structural similarity. Next, please. As far as objective evaluations. Subjective evaluations, not very surprisingly, is based on mean opinion score, where you have people that measure the quality, judge the quality of pictures in a scale of 1 to 5. These things really need to be specified, not only in the scale, but also the actual conditions, what monitors you use, what colorimetry in the monitors, how far people are sitting away from the displays, et cetera, et cetera, et cetera. And so that's what we mean to outline here. The subjective evaluation should be based on MOS, but we should have to be careful as to how that is exactly defined so that we could use it reliably through time. Next, please. And so finally, conclusions. So the document that we've submitted, the version 2, has an overview of the internet video coded applications and typical use cases. There have been some comments that we should evaluate after this presentation. And then we would like to recommend that we have an evaluation framework, both objective and subjective, and move forward. So that's it. Any other questions?
Great, thank you very much. So this is the second time we've looked at this stuff in this document. Who actually has had an opportunity to read through the existing requirements document? Okay, not an awful lot of the room, but I do want to go ahead and push on to the second part of the question here, which is, so this looks like it's forming a basis for our requirements milestone. And I want to get a sense of the room that we can confirm on the list as to whether this is something we want to adopt as the working group item, meaning we would take this draft as the basis for the working group requirements. So I'm just going to do it hand raises because there's not enough people who read the document to really take hums on this. So in favor, up. Okay. Anyone object to taking this as the basis for our work? Up. Okay. It looks like we have consensus in the room to adopt this. We'll go ahead and confirm it on the list, but I think this is probably going to be a working group document moving forward.
Great. Thank you.
So thank you for your time.
Real quick, Tim, do you know if Jack got everything that he wanted to get from his original requirements document into this document? And if not, would he be willing to work on the workgroup draft version of this?
I believe this contains everything that he would like to see, so there's no additional things you need to move over.
Cool, thanks. So Thomas.
Yep, Thomas Stady, Mozilla. This is my second O2 draft for this, so I'm just going to go over the changes from the previous one that we talked about. So the first thing I did is I defined new bitrate ranges. We're doing the MOS score test, we're doing the BD rate scores, and previously we had a couple of rates picked in, but we were just using the entire curve. So now with the requirements draft, we have 3 ranges, and those are defined in mind. So I chose these basically picking, they're in bits per pixel, which means that they scale down and up based on how big your video is. So most people don't deal in bits per pixel, so these are basically for 1080p 24 frames per second video. This ranges from about 250 kilobits per second on the way low end, and then the very highest end, this is about 10 megabits per second. And then I divided the ranges basically by they're about logarithmically equal sections, and then I just picked, that gave big numbers, so I gave nice round numbers. So on the next slide, there's a picture of how they're distributed, and that does not show up at all in the projector. Yeah. That's okay. But the idea is that they're basically on our graphs that are logarithmic scale for bits per pixel. You see 3 about equal sized chunks that are basically the low bit rate is for video conferencing, low motion talking heads, medium bit rate for kind of YouTube applications, and then high bit rate for higher quality streaming. Yeah.
Okay, there's a question from Thomas Davis. What about frame rate? 60 Hertz does not require 2 times the bit rate of 30 Hertz.
Yeah, so bits per pixel currently scales counting frame rate, so that means it will actually use twice. These ranges will now be twice the bit rate for 60 frames per second. For actually 24 to 48 to be twice. So that might be something to consider actually. Instead of defining these on bits per pixel, it could be just the bits per pixel per frame, but then not also scaling with the frame rate. I'm not sure exactly. We'll have to figure out how much we actually want to scale that, because I mean, higher frame rate does require more bit rate, but it's not necessarily twice as much as BPP would scale. So we might want to figure out some intermediate scaling there. All right.
Mosinati, get back one. Would it be useful to put the actual bit rates of the content instead of the bits per pixel here, because I think people may relate to it better?
We have there's a ton of different resolutions, which is why I didn't want to go through and specify all the bit rates for all of them.
Okay.
Because especially for if we're doing screencasting all sorts of weird video sizes. But if we actually end up, once we figure out the final test sets and everything, and actually have a list of resolutions, so we could actually pick ones.
Yeah, maybe for the very high runner, very high runner resolutions that we want to make sure are explicitly tested. We should just put in the explicit bit rates for those, because people may relate.
Or we could actually just figure out what is reasonable for those, and then interpolate all the other ones in between, or something.
So there's another comment from Thomas Davis. He says square root is okay for frame rate.
Okay. Yeah. All right. Another objection was that on the previous draft, I have basically two profiles to run the codec in. One is the high latency mode, which is for basically YouTube streaming and storage, where you have many B frames, etc. And I had then the constrained low latency, which had the low latency constraints, but also had a bitrate reservoir constraint. So it had you're required to use basically closed loop rate control on it. The concern was that using the rate control would require your codecs have to have the rate control implemented to be able to use a test. B, it could introduce a lot of noise into the tests. because the tuning for that control is basically super dependent on the particular test sequences we use. So I have added a new mode called unconstrained low latency, which is basically exactly the same, but it does not have any sort of constraint on bit rate. It just says use the best possible quality you can. So it's I have examples of how to configure the codecs on the draft. If you have a favorite codec, you should probably go look at the parameters and make sure that they look reasonable. But in the case of Dala and Thor, they are actually identical to the high latency case because neither, well, actually Thor now does have this, but until very recently, both only operate in low latency mode. So this also means that now the constrained low latency mode is not actually referenced anywhere. I still have it in the draft, but we might want to actually take it out if we can't find a way to actually use it. So I have not figured that out yet. Next. Oh, the other thing about this is that, importantly, this still allows rate control to be used. It just does not provide, it removes a bunch of constraints. So the model of the encoder is still black box. We don't actually tell it can't do things. We just, from an external point of view, say that the latency is limited and basically everything else is not limited. Okay, next slide.
Just to clarify again, so your new unconstrained low latency is unconstrained in every way except zero structural delay?
Yes.
That's the intent?
Yes. So there's a new ABX subjective testing section. This is basically based on the implementation on already compressed yet, which is only for images. This actually works just as well for videos. We haven't implemented it yet. It's a very simple ranking. You look at two images in a reference and you decide which of the two images at the same bit rate looks better. And that's what we actually use all the time for comparing very similar changes that disagree on metrics. There's no way to actually, we want MOS scores. We have currently no way to do that. So that is something that still needs to be implemented. And I'll probably, once I get an actual working implementation to be able to test it, I will probably put that in the draft. But that is still missing. There's a couple other unresolved issues I'd like to talk about. This is the same as the previous draft. All the metrics are chroma plane, sorry, I should say luma plane. But sorry, all metrics are luma plane only. Which means that they totally ignore chroma, but all of our test videos are 420 with color information. This means that basically you can kind of cheat on the metric just by not coding black and white images because the metrics can't tell the difference. So there's a couple of options to this. One is to use metrics that take into account chroma and luma, but there aren't actually very many good metrics that do so. At least we have not found any. There's a couple people on our channel actually working on some. But the other option is to actually use only black and white test sequences for all of these, which removes that, is not actually how the codec is being run, which is a little bit unfortunate, but removes this variability. Okay,
Okay, I have again a comment from Thomas Davis. It's quite long. I hope to, well, let's at least read part of it. Main comment, the draft does not state what the testing is for and what the best test methodology might be for each purpose. Can you clarify the purposes you have in mind? What you might do for final testing is different for what you might do for testing a tool for inclusion, for example. This draft seems aimed at final testing rather than the process of developing the codec. I'm concerned about sucking away a lot of effort into developing fancy two-pass encoding methods and rate controls that don't improve the fundamental technologies at all when we are doing tests just for deciding on tools and judging current progress. We really want to constrain adaptivity to make fair comparisons between different codecs also.
Okay, yeah, so this is basically talking about, on my previous where I mentioned it as a black box model, that basically means that all sorts of rate control, such as basically adaptive quantization and sort of like temporal rate control that doesn't use any look ahead, it can still work. So I am I am basically undecided about that. I would prefer not to actually, basically the problem is if you actually tell codecs they can't use certain features in their encoder, then you have to be very careful to make that fair as well, because you have to make sure a lot of codecs don't have equivalent features. The most obvious one is for adaptive quantization. DALA does not code an adaptive QP, basically. It has, as part of its quantizer. So you can find it, for that one, you can find a sort of equivalent feature in that you change how our quantizer works to get a similar result. But I'm not entirely sure that you can totally make it equal anyway. I can attempt to make something. I'm not sure it's always going to be useful, especially for a lot of the fancier metrics. Like PSNR likes to turn everything off, but a lot of the newer metrics actually respond correctly to a lot of these things. So,
Mosinati, I think what Thomas was pointing out is probably a good thing to figure out whether or not we should have a separate section in the test doc for. And it's basically whether it's really two different types of testing. It's, one is like beauty contest testing to show, what the NetVC codecs, look like compared to external codecs, or maybe different candidates, look like to each other, versus, constant iteration of working in the group to, to progress a single candidate once we ever get there. And it may be useful to have a split in the doc for different test cases for those two cases, because I could see some value in a more, a more holistic test that's, for window, for beauty pageants, and then a more rigorous and constrained test that tries to, isolate factors and minimize variables to do, iteration work. So I think it may be good to have two separate sections of testing like that in the doc.
Yep. The other thing that actually happens if you're looking at inserting a tool, we had the whole concern about, what is fair to compare two codecs. But if you're talking about inserting like some new tool, then you're comparing the codec to itself, and all those concerns basically go away because it's the same codec. So we can talk about within a single codec about, what features might be, we want to turn off to, amplify the effect of something else. But again, that's very codec specific, so it's hard to me to do from a. I can go in and start doing codec specific stuff.
Well, I think the one that's general, that we already know is an issue is the rate controls. We already know that you can get, outlandish, gains by doing some outlandish rate controls. And so it would be good to separate that one variable out and show that, look, when you're doing constant iteration, we don't want to have the rate controls on for those cases.
Yes, you're talking about not certainly the closed loop, but the open loop where you essentially guess based on history, right? So
if you do adaptive quantization, you do, premium frame pulsing and things like that. There's known techniques that can get you, 15, 20, 30% gains, way beyond any gains that you're going to get from most other coding tools. And they have nothing to do with the codec, right? You could do it on any codec, and we wouldn't want that to mar the results of a tool selection or a candidate selection.
Yes. Of course, the other problem is that they then have different results on different codecs based on how the codecs are designed. So then that also kind of creates more variability. But because I know then we have to actually specify like exactly what quantizer we are allowed to use for that. So that becomes also kind of hard because there's also many other features besides quantizer, like you can change lambda. So we have to specify for other features as well that do RDO. It's certainly possible. I can look into doing it if we think it's important. So I would still very much like to have these kind of unconstrained black box scenarios, I think, for final testing, because I think if we produce a codec in the end and then the encoder can't do any of these things, that doesn't make it useful, because these things are, actually do make the codec better. Maybe for comparing tools and stuff, we now talk about how to, basically kind of turn them off, or we look inside the black box. But I would also like to have the ones where we actually just look at it as a whole.
Yeah, I agree. We should have both the iteration testing and the final or black box testing. One final minor comment on the chroma, Luma only versus including chroma. I thought at the last meeting we were considering just having a simple weighted, weighted average of all of the planes, you know, the
Yeah, so that works. Okay.
6/8, 1/8, 1/8.
That kind of makes sense for PSNR, but no one really knows exactly what the weight should be. It doesn't really work very well for the other ones.
I think, you know, a weight of 0 for the chroma is, we know, is not the right weight.
Yeah.
So any weight higher than 0 would be a good start.
So some of them have done it actually in RGB space, which makes it makes it, you know, a little bit more obvious what to pick. But in the end, I'm not sure if that also is actually useful.
Yeah, Tim Terrier from Mozilla. So you also don't necessarily have to do a weighted average, just report all 3 scores.
Yeah, and again, that works for PSNR. It's not so good for the other ones, but
it's probably not terrible for PSNR HVS either. It's SSIM and fast SSIM where it's essentially useless, at least the way it's implemented in our current tools.
The other thing that I have is I actually have the draft actually includes, if you look at it, has a list of actual videos and test sets that we have on our server. Unfortunately, I actually have a bunch of new 1080p and 4K, especially footage, that I came after the draft deadline, so I don't have it in there yet. But that is coming soon, and I would always like more of it. So if you have a big source of 4K test footage that you like to use for your internal testing and you contribute it, that would be great. That is actually it as far as changes from the last draft. So if anyone has any additional questions.
Okay, thank you very much.
Cool.
So similar to the requirements draft, this is the second time we've seen this up in front of the room. There's not a competing draft out there, so I'm going to go ahead and just ask the same question about who has had an opportunity to read this draft. Hands, we've got about the same crowd. All right, and who thinks we should adopt this as the basis for the working group milestone for testing? Okay, and do we see any objections? Hands up now. No, okay, great. Making good progress here.
Martin, real quick, is anyone in the Jabber room mentioning anything about adoption or not? You getting any comments from the Jabber room about adoption or not?
So we'll confirm that on the list, but it looks like we have good support for both of these. All right. Now Jean-Marc's going to talk to us about D-ringing. Do you have a new version of this?
No.
Okay.
So I'm Jean-Marc Vanin from Mozilla. I'm here to present a new de-ringing filter that we added to the DALA codec recently. Slide. So first, what is ringing? It's a type of artifact in video codecs where edges tend to have oscillations around them, which makes it very annoying visually. So we're trying to remove that. Overall, the design goals of this de-ringing filter, so first was obviously remove ringing artifacts, but in doing so, we want to make sure that we still preserve sharp edges and also any texture we don't want to end up being blurred. It also had to have reasonable complexity, which eliminated some preliminary algorithms. And last, we want the algorithm to be easy to vectorize, so implement in SIMD. That's pretty important. Next slide. So these are the basics, the basic algorithm of the de-ringing filter, and some steps I'll explain later what they mean exactly. So the de-ringing filter works on a super block at a time. So for each super block, we look at the ones that are skipped, and those we just do not do anything because skipping usually does not add blocking artifacts. Of the blocks that are skipped, we actually code a flag that says whether we actually run the de-ringing filter on that super block or not. And on the super blocks for which the deringing filter is run, then we look at individual 8x8 blocks to see which ones have been skipped by the encoder. And on the ones that are skipped, we also do not run any deringing, again, because there's nothing to dering. So of the remaining 8x8 blocks that remain that we want to dering, the steps are essentially, first, we estimate a direction for each of these blocks. From there, we estimate thresholds that control how aggressive the deringing will be. Then there's a deringing step along the direction that we found, and a second deringing step in the direction across. And I'll detail exactly what these steps do. Next slide. So first, direction information. This is something that the decoder does in parallel with the encoder. So none of this information needs to be signaled. It runs on the decoded image directly. So the idea is to try each of 8 possible directions, and for each of them, we replace each line along that direction with the average from the decoded image. So we see an example here for one of the directions. All of the blocks, all of the pixels numbered 0 would have the same pixel values, 1 would have the same pixel value, and so on. And we compute the distortion between that directional version of the block and what the decoder output. We compute that distortion for each of the 8 possible directions, and the one with the least distortion has to be the actual direction of the block. It sounds complex, but there's lots of algebraic simplifications that make it reasonable to compute. So that's the direction. Next slide. So the second step is finding the threshold. The threshold we're going to use for the next filtering steps are basically estimates of the amplitude of the ringing. So we want to know if we're seeing oscillations around this amplitude, is this ringing or is this actual details that we want to keep? And so these thresholds depend mostly on the quantizer. So the lower the bit rate, the larger the threshold. But it also depends on the amount of variance in the super block and in the local block. So if we've got lots of edges, then it's likely that we'll have more ringing than really smooth texture. So that's for the threshold. Next slide. Once we have the threshold, we can use it to compute what we call conditional replacement filter. That filter is somewhat inspired from both median filtering and bilateral filtering. And the main idea again is we want to be able to smooth out the ringing without smoothing out the edges. And the way we do that is we compare each tap, the pixel at each tap of the filter, we compare it with the center pixel that we're filtering. And if the value is close enough to the center pixel, that's what we use for that particular filter tap. If it's too far, we replace it with the value of the center tap. So I've got an example here with 7 points, and the one we're trying to filter is the one in the middle with value 25. So if we were to apply a dumb filter with all weights equal to 1, we would end up with a value of 29 instead of 25, which is not really what the neighbors' values are. But what we do instead is we compare with the threshold. In this case, for this example, the threshold is 5. So there's 2 values that are sort of outliers that we assume are not due to ringing. So these 2 values in red, we replace with the value 25. That was the center pixel. And then we can compute the actual average, which in this case would give us 24, which is closer to what one would expect for a deringing filter. Next slide. So in the previous example, all the weights, the filter weights were 1. In practice, we can use weights that are different from 1. One important thing there is that unlike bilateral filtering, when we simply replace a value with the standard pixel, we end up having to divide by the sum of the filter weights, which is a constant. So we don't need to divide by something variable. We don't need to compute the what the normalization factor is. So this makes it a lot easier to implement, and especially a lot easier to vectorize than a bilateral filter. Especially we can choose whatever sum of weights we want, so we can pick powers of 2, which makes implementation even easier. And so also in a practical implementation like we do in Dala, instead of actually replacing pixels with the center pixel, we can simply work directly from the difference between a standard pixel and each of the filter tabs. So we simply accumulate differences, or we accumulate zeros. So again, this makes it really easy to vectorize, so we can essentially filter an entire line at a time with a vector. Next slide. So this here shows an example signal on which we can apply this conditional replacement filter. So up left, we see the original filter, the original signal that has, gradients, edges, and some texture. In the picture below is that same original signal plus some noise that was added, just like you would have from quantization noise. And so in the upright is what would happen with a really dumb low-pass filter that would be 7 taps long. So it definitely gets rid of a lot of noise, but it also completely smooths out the edges, and also the pattern in the middle becomes completely flat. So that would be unusable for denoising or deringing purposes. And bottom right is what the conditional replacement filter does. So most of the details are still preserved, but a lot of noise is gone. And this is pretty much what we're trying to achieve here. Next slide. So as I said earlier, the filter is first run in the direction that we identified in the first step for the block. And so this is an example. In this case, we identified the direction as being 45 degrees upright. So we'll run the filter on every pixel. In this case, we show the pixel being run on the pixel that has number 25 there, just as earlier. And we look at the filter taps along the direction that we identified. Again, some values are replaced with the center pixel, and we do the averaging. We do this step for every pixel in the block. Some of the taps will fall outside of the block that we're filtering, and it doesn't really matter. We just pick them from outside the block in the image. Nothing special being done there. So there's no special thing to do about edges. Next slide. So after we've dering in the direction of the pattern that we identified, there's a second filtering step that is performed across the main direction. The goal of that step is to further dering the smoother backgrounds. And this is the first one was a 7-tap filter. This one is a 5-tap filter. And it uses a threshold that is much more conservative. So there's less, we know that we're going to be deringing across edges. So we want to make really sure that we're not blurring out these edges.
Moses and Natty from the floor. I got a question about the thresholds. So first, do you have a threshold or an aggressiveness for the direction determination, not for this more conservative threshold? Do you have a threshold for the directionality aggressiveness or something like that first?
So the first threshold that I mentioned is the one that gets applied to in the direction of the filter. So for example, at a certain bit rate or something, maybe the threshold will be 30. So I run the filter along the direction. So running it along the direction means that it's less likely to encounter an edge, because if it's parallel to the edge. And so that aggressiveness depends on the factors that I mentioned earlier, like what's the quantizer level, like the bit rate, and how much contrast there is.
Okay. So it was actually two questions. I think you're answering the second part. So yeah, I was curious about what the threshold values were, how they're computed, are they adaptive or not? So they're not adaptive. They're just directly derived from the current operating parameters or something. They're not adaptive to the content.
Yes, they are also adaptive to the content.
They are adaptive to the content.
They depend, as I said, on the bit rate mostly, but also we use what we found in the direction. The direction estimation kind of measures the variance in the block. So we use that variance to also change the thresholds. Like if we have a really sharp edge, we expect more ringing, so we use a larger threshold. And if everything is really smooth, then we use a lower threshold.
Okay, so the variance of the block is compared to this threshold, or the variance of the block determines the threshold?
The variance of the block influences the threshold.
Okay, and then that's the second part of the question that I was trying to ask. The first part though was that, does your direction determination, does that have some sort of aggressiveness or conservativeness or adaptivity to the content to figure out how your confidence level in the direction, basically?
Oh no, it's fine. It really finds, like, if I had to pick a direction, this is a direction. And it can be, sometimes there's no real direction, and in that case it doesn't really matter. And even if you get the direction wrong, it's not the end of the world, because you still have the threshold to prevent blurring. Like if you use a fixed direction, always horizontal, things are still going to work. Not nearly as good as with having the direction, but it's still going to work because the conditional replacement filter will still avoid blurring out the edge. It's just that you'll get mostly less deringing because you'll have fewer taps that are useful.
Yeah, Tim Terrier from Zillow. I just wanted to clarify, like, we basically always pick a direction. There's no non-directional mode.
Yeah, okay, so continuing on with the second step of filtering across directions. As you see here, in this example, we are filtering between 5 different pixels, which were each computed from 7 different taps in the image in the first filter. So effectively, the support of the final deringing filter is 35 taps, which makes it possible to remove a lot of ringing when you're not very close to an edge. And even when you're close to an edge, you still have many of these taps that are actually usable. Question?
Steve Botsko, this one is orthogonal to the direction, or this is vertical and the direction was 45 degrees? I'm a little confused what you mean by cross.
Yeah, so the idea is to be sort of orthogonal to the direction, although in this case, you don't want to be perfectly orthogonal because you want to pick all the lines. In this particular example, if we were going 45 degrees orthogonal, we would have 2 lines, but we'd be skipping pixels that are in between these 2 lines. So instead, we use either vertical or horizontal depending on what we did for the first filter.
Okay. And if the direction had been horizontal?
If the direction for the first had been horizontal, the second would have been vertical. If the first had been vertical, the second would have been horizontal.
So this is always either horizontal or vertical.
It's
no matter
always
what
either
the original direction was. It's just you pick the one that you do
the closest to being orthogonal.
Yeah. Okay.
Next slide. So this shows the kind of results that we can achieve with this deringing filter. So maybe you can skip back and forth between this slide and the next. So this shows without deringing, with deringing. I don't know how visible it is with this. It's clearer from the directly on the laptop, but this is really extreme bit rates that like extremely low that we probably don't use very much in practice, but it's easier to view in projector. It's also useful at higher bit rates. So next slide. In terms of objective results, we ran this through our NTT short test set on Are We Compressed Yet? Over a range of reasonable bit rates between 0.25 bit per pixel and 1.2. We got about a 6.5 BD rate, 6.5% improvement in rate for PSNR and 4.7 in PSNR HBS.
Stefan Mitskogin. Do you have any numbers for lower bit rates? All those bit rates are quite high.
Oh, so it continues to be around these kinds of values for lower bit rates. At some point it drops off a little bit, but it, as you saw in the previous example, even at pretty low bit rates, it's a clear improvement. At some point it'll fall apart, mostly because you know, it becomes just a bunch of blocks of different colors and the directional patterns are no longer very clear. But
Steve Batso again. So this is in the prediction loop. That's why you're seeing gain.
I'm sorry?
So this is part of the prediction loop, basically. The decoded image after you run this filter becomes the basis for the...
Yes, it's run in a loop, yes.
Yeah, okay.
The improvements on still images are kind of similar as well.
Yeah. Is there any situation you found where it would be useful perhaps to run it outside that loop as a post filter?
I don't think it would be a really good idea. First, because it always improves the prediction, because if it weren't improving, we would signal it off. We always have the option, if it makes things worse, we don't use it.
This is block by block, you turn it off?
No, the decision is super block by super block, but we only code the decision on super blocks that for which we actually coded something. If we skip the entire super block, we're not coding the decision and we're not deringing.
Stefan Mitskogin again. Is there a typo there? Is the number on the top off by a factor of 10? There's a difference between what we write there.
Sorry, yeah, I'm sorry.
So which one is the correct one?
These are off by a factor of 10, yeah, and I understand now why you commented it was really high rate. No, this is 0.025 bits per pixel to 0.12 bit per pixel.
Okay, thanks.
Yeah, sorry. Sorry about this. Yeah, so, question?
Thomas Davis again. Have you tried running the filter on a subset of frames? Example given, HQ frames in a frame hierarchy would reduce complexity.
I'm not sure I understand the question.
I think he's asking about the complexity of the technique.
Oh, the complexity. So we did SIMD optimization of the whole thing, and I think that maybe Michael has the final complexity. With how many percent of the? So 5% of decoding time right now is spent in the deringing filter. That might increase a little bit once we optimize the rest of the decoder.
A little bit more, and I think I understand the question myself now. So the question is, have you tried using this technique only on a subset of frames? Yeah. So for example, only every 4th frame or so, you would use this to reduce complexity.
No, I've not tried that.
Okay.
Maybe it's something that's worth trying. I have not. So, yeah, and we also tried experimenting with Thor and comparing. Like we tried taking the Thor constrained low pass filter, which does something a little bit similar to this deringing filter. And we put it in DALA to compare what the performance was. I have to say this is early work, so it's quite possible that we made errors, and we made some in the first runs. And also the constrained low pass is much lower complexity than our deringing filter. So take these with a grain of salt, but the curves here, oh, yeah, one of the curve is really hard to see. Essentially, the constrained low pass filter is very close to the deringing filter line at high bit rates around, oh, we see it here. So on the high end, the constrained low pass is very close to the deringing curve, and it becomes further apart at lower bit rates where the deringing filter seems to work better than constrained low pass. We've also been trying the exact opposite, running the DALA deringing filter inside Thor. I think the experiment is running right now, or it's almost done, but we don't yet have results. Visually on still images, the deringing filter was providing noticeable improvements, but we're still not done running it on video, so we need to experiment a little bit more there.
And what was your test set? What was your sequence test set that you were using?
In this case here, it's our set called NTT short and are we compressed yet. It includes a bunch of videos at different resolutions. It mixes video conferencing type clips with like movie type clips.
Because the visual example that you showed earlier, that's part of the test set?
No, the visual example I showed earlier is part of a separate test set of still images that we have. It's not in these curves here. These curves are actual video.
It'd be interesting to see these results for classes of classes of sequences. We can see the the behavior on natural content, the behavior on texture-rich content.
Yeah. Well, so across this particular test set, I went through each of the clips, and the filter pretty much improves all of them. And again, when we compared to the constrained low pass, the deringing one was better than constrained low pass on every clip, basically. Not always by the same amount, but it was performing better, at least in DALA anyway, assuming I haven't made any errors in the constrained low pass implementation, which is still possible.
So, Tinterio from Mozilla, just to respond earlier to Thomas Davies' comment. So running every fourth frame, I think, would present some difficulties just because you have to, you'd have some complications of tracking which areas were actually skipped and which ones had been updated in the intervening frames. And, that's important for reducing the signaling, right? Because we don't want to signal to run the filter on areas we know we've skipped. But you could certainly do it if you were doing something like hierarchical B frames. If you just run the filter on the IMP frames and skip it on the B frames, or maybe only the top level of the B frame hierarchy, that would be perfectly reasonable. And we always have the option in the encoder side to just disable the filter on every block. And if you disable it on all of them, because we have entropy coding, that will be relatively cheap. It would cost you a few bits per frame.
And also in terms of complexity, we're not actually running the filter on every super block, because many super blocks end up being completely skipped, so we don't run the filter on these blocks.
Yeah, generally in your B frames, you're skipping most of the super blocks anyway, so you're almost already doing that.
Yes. Well, assuming we had B frames. So that's it.
So it's good to see this tool, and I think this is a good example of something that we'd like to do going forward. the constrained low pass filter in Thor is something similar to this, and trying to achieve a similar goal. So it'd be really good if you and Steiner could, both talk and work out what you think, conceptually some of the differences may be, where the gains may be coming from. Is it maybe a classification? Because I think the Thor doesn't do much classification. Can we figure out if we could use some parts of this for classification and maybe improve the Thor constrained low pass, and figure out how we can balance the complexity and the gain trade-offs to arrive at something that both candidates agree is the best common approach for this kind of a tool.
Yeah, there's definitely more experiments to make there. I think maybe the most fundamental difference between the two is that the constrained low pass filter is, as the name implies, constrained to changing pixel values by only one. So at the high bit rate, this is actually working pretty well. Whereas at low bit rate, the deringing filter can change values by more, so it can have more of a direct impact. But yeah, that being said, like I've tried dumbly applying both. That didn't work. But yeah, we can probably get to something somewhere in the middle that works nearly as well, but it's less complex than.
It'd be great if both authors could get together and brainstorm a little bit about how we could arrive at a common tool that would help both codecs out.
Yeah, definitely.
Steinar Midtskogen. The performance probably also depends on other things in the codec, like what kind of interpolation filter you're getting, and so on.
I'm sorry, what kind of?
The result probably depends on what kind of interpolation filter we have in the codec. So what works in Dala might not work in Thor, and vice versa.
Yes, we're trying to investigate that. What I suspect would make even more of a difference is the fact that Dala does not have an intra-predictor, whereas Thor has an intra-predictor, so it currently does a little bit better on edges. So there's probably less of a need for deringing, although we're still seeing some improvements on Thor still images. I can show you some of those that we generated. But yeah, I don't expect the difference between constrained low pass and deringing to look the same when applied to Thor than it does when applied to Dala.
All right, great. So, thank you very much. And I believe that's all we have for today. Do you have anything else you want to add? Or
just that tomorrow's session is going to have only updates on Dala and Thor. So if you're not familiar with some of the basics, I strongly encourage you to go through the 93 proceedings. You'll get a good overview from those presentations. You will not get an overview in tomorrow's session. They'll just be updates. So if you want to follow along, please look at the overviews from 93.
And the last thing is, if you have not signed the blue sheets yet, please stop by the chair table and sign them before you leave the room. Thank you very much, everyone. Finished a bit early.
Way early before.
Yeah.
Jean-Marc will pay over his time, but everybody else went way under.
We're supposed to be done, what, in 15 minutes?
10.
10?
5 minutes.
Oh, wow. We made up being behind. Which has never been a concern before.
Jean-Marc started like 15 after.
Yeah, I know. There were a lot of questions on it. That's good.
I mean, it's the first one that's really good. And it's cool if they've been able to play around with two different, both code bases, same kind of tool.
You have to sign these? There's an implication if you have a director in here. That's sure. What, for company, name, or both?